First-generation blockchains, like Bitcoin, were designed to solve a single problem, creating a decentralized ledger to transfer scarce value without a trusted intermediary. Then came the second generation. Ethereum introduced a programming language to the blockchain, allowing users to embed customizable terms and conditions directly into their transactions through smart contracts. But as these networks attracted millions of users, they hit a mathematical wall. They treated growth as a one-dimensional metric of adding more blocks to a single chain. The result is a strict architectural bottleneck. Networks slow down under limited transactional throughput. They remain completely isolated from other blockchains, and they rely on finite funding models like initial coin offerings that eventually run dry. A protocol cannot serve as the backbone of global finance if it physically congests under heavy load, cannot communicate with legacy banking systems, and inevitably runs out of the capital needed to maintain itself. Cardano is a third-generation architecture. Instead of patching the legacy code of older networks with ad hoc forks, it was built entirely from first principles to solve these systemic flaws. The foundation of this design relies on formal scientific peer review and high-assurance code. This is the exact engineering standard applied to aerospace and medical software, where a single system failure can result in human death. The architecture is engineered around three specific pillars: scalability, interoperability, and sustainability. This framework shifts the development focus away from launching experimental, single-use tokens. It treats the network as permanent, mission-critical infrastructure. Approaching blockchain as a strict systems engineering problem is the only mathematically viable way to build a network capable of supporting billions of concurrent users. Scalability is often reduced to a single metric, transactions per second. But true scalability requires expanding three distinct resources simultaneously: compute, network bandwidth, and data storage. In earlier networks, the compute bottleneck stems from proof of work. Every node on the network races to solve complex cryptographic hashes, wasting massive amounts of time and electricity to construct just a single block. To bypass this waste, Cardano uses a peer-reviewed proof-of-stake consensus protocol called Ouroboros. Ouroboros is an algorithm that secures the network by selecting block creators based on the amount of cryptocurrency they hold, rather than their raw computing power. Ouroboros breaks time into distinct epochs. Within these, it randomly elects slot leaders to validate blocks, removing the energy-intensive hashing race. Because the computational cost is virtually zero, these leaders can run transaction processing epochs in parallel. By removing the artificial computing race, the transactional capacity of the protocol naturally scales in tandem with user growth, rather than degrading under its own weight. The second resource is network bandwidth. In standard TCP/IP peer-to-peer meshes, every node must relay every message. As transaction volumes rise into the hundreds of thousands, this homogeneous structure forces the network to crawl. Cardano addresses this using recursive internetwork architecture, or RINA. RINA is a structural networking model that uses distinct policies to manage how data communicates across different layers of a system. Instead of forcing every node to handle the same data, RINA creates a heterogeneous network. It dynamically routes information through specific pathways based on the exact hardware capabilities of individual nodes. Finally, blockchains store ledgers forever, growing from gigabytes to petabytes, locking out standard consumer hardware. To prevent this, the architecture uses distributed partitioning. Similar to a BitTorrent system, users only store a small fraction of the total data to maintain security. Combining the compute efficiency of Ouroboros, the routing of RINA, and cryptographic data partitioning creates a system that can expand its capacity infinitely without ever centralizing its hardware requirements. The next pillar is interoperability. Isolated blockchains fragment global value. This isolation forces users to rely on centralized, highly fragile exchanges to act as gatekeepers between different networks. Cardano bridges crypto-to-crypto communication using non-interactive proofs. These proofs compress a blockchain's entire state into a tiny file, allowing an entirely different chain to mathematically verify a transaction without downloading the original ledger. But bridging to traditional banking networks presents a different hurdle. Legacy finance requires strict compliance, identity attribution, and anti-money laundering checks. Broadcasting this personal data transparently on a public ledger is legally and practically dangerous. The solution is an opt-in feature called metadata encapsulation. It securely attaches contextual information, like the story behind a transaction, to a digital transfer without exposing that data to the public. A user can attach encrypted, private metadata to their transaction. This data remains completely hidden from the public network, but can be securely revealed to a regulated bank node when escalating funds out of the crypto ecosystem. True interoperability requires the architectural ability to selectively apply legacy compliance to permissionless networks, moving value seamlessly without sacrificing base layer privacy. The final pillar is sustainability. Early protocols relied on massive, one-time influxes of capital from initial coin offerings or patronage from large corporations. When that money runs out, development stalls, and corporate influence inevitably centralizes power. Cardano replaces this with a protocol-native treasury model. A specific percentage of every newly minted block reward is automatically diverted by the system into a decentralized bank account through built-in inflation. Token holders use a liquid democracy voting mechanism to decide how those funds are spent, directly funding ongoing development, marketing, or scientific research proposals. But funding is only half of the sustainability equation. The other half is governance. In older networks, irreconcilable disagreements over code updates frequently lead to destructive hard forks, violently splitting communities and diluting network value. To resolve disputes mathematically, Cardano relies on formal verification. It is a process that uses mathematical proofs to guarantee that a system's underlying code perfectly matches its intended design and behaves exactly as specified. Future Cardano improvement proposals will be written as machine-understandable formal specifications. Instead of debating the intent of an upgrade, the network clients themselves will be able to mathematically self-verify if they are complying with the new protocol rules. A blockchain can only survive long-term if it contains internal, automated mechanisms to fund its own evolution and objectively resolve its own governance disputes. Scalability, interoperability, and sustainability are not patched-on afterthoughts in this framework. They are engineered as interlocking base layers. A legacy bank initiates a compliant transfer, bridged via encrypted metadata into Cardano's routing layer. Data routes through RENA topologies to a slot leader, validating instantly without wasted energy. Finally, a fraction of the fee routes to the treasury to fund the protocol's next iteration. Isolating these specific vectors into distinct, specialized layers marks the crucial difference between an experimental token and an enterprise-grade protocol. The ultimate goal is not to create a single ledger that rules the entire market. The goal is to build an interconnected Internet of blockchains where value flows freely across entirely different ecosystems. Constructing those bridges requires a foundation of high-assurance code and rigorous peer review, ensuring the infrastructure will not collapse under the weight of global finance. The Cardano framework represents the maturation of cryptocurrency. It shifts the industry away from fragile, speculative applications and establishes the blueprint for permanent, self-sustaining global financial infrastructure.